There's an idea that I wanted to help you understand. It's called rationalizing the denominator. Whoa, what in the world does that mean? Well, it's a technique that we need to use as we kind of advance into some other math that we're going to have down the road. And it basically means that anytime I have a solution where the denominator will include a radical, we're going to say that that's not reduced. Anytime there's a radical in the denominator, we're not all the way simplified yet. So how do we simplify it? We learn a technique called rationalizing the denominator. Basically what it means is I'm going to multiply this fraction or this rational expression by a very clever version of 1. And remember, why can you multiply any fraction by 1? Well, that fraction maintains its same value. It maintains its equivalency. So I'm going to multiply this by something such that the radical disappears in the denominator. Can you think what that might be? What about if I multiply the denominator by a root 3? In order to do that, I need to convert that into a clever version of 1. So I have 1 over root 3 times 1, but the version I'm using is clever. I'm going to use a root 3. So what happens when I do that? 1 times root 3 is a root 3. The denominator is root 3 times root 3, which becomes square root of 9, which reduces down to a 3. So root 3 over 3 is simplified. Yeah, I know. It may not look simplified because 1s always feel so much more simplified than not, but the radical is no longer in the denominator. There's 1 in the numerator and that's fine, but I'm mostly concerned what's in the denominator, and there's no radical there. So let's look at another example. Let's look at root 5 over root 6. It's not simplified because I have a root in the denominator. Therefore, I'm going to use this technique called rationalizing the denominator. So I'm going to multiply this by something, a clever version of 1, that the root 6's will disappear in the denominator. What's your clever version of 1 you're going to use? Well, I'm going to use a root 6 over root 6. Again, just multiplying this expression by 1. Root 6 times root 6, the denominator just becomes a 6. The numerator becomes a root 30. And I might check to see if that reduces down. Are there any factors of 30 that are a perfect square? 4, 9, 16. Nope, I don't see any perfect squares, so now I am completely reduced. This one might be a little tricky, and the reason why it's going to be a little tricky is because we're going to be in cube root world now. So to rationalize the denominator in cube root world, we need to be thinking about perfect cubes, not perfect squares, to help us to determine what our clever version of 1 will be. So let's first of all recognize it needs to be rationalized. And I recognize that because this is really this cube root of 7 over the cube root of 25. Need to find out what's my clever version of 1 to make the denominator a perfect cube. If I can recognize that my denominator, and I might write it like this way, I recognize my denominator is a 5 squared. I really need to be a 5 cubed in order for it to have a perfect cube in it, correct? So now my clever version of 1 is a cube root of root 5. Because when I multiply those out, and I'll come back down here, when I multiply those out, cube root of 7 times a cube root of 5 is a cube root of 35. The denominator becomes a cube root of 5 cubed, or 125, whatever way you want to write that. And we chose that clever version of 1 because it's clever, because it makes the denominator radicalless. So I have the cube root of 35 on top, and on the denominator, I have the cube root of 5 cubed, which just becomes a 5. There's no perfect cubes in 35, so that's simplified, and there's nothing else I can do. I can't divide this 5 into that 35 because that's really a root 35, a cube root of 35. So I am done. I am simplified on that problem.